Hello, everyone. Welcome to this week's Crunch seminar. Today we have one speaker, Joongoo Jeon. Joongoo is an assistant professor in the Department of Quantum System Engineering and Jeonbuk National University in Korea. He has been the director of Korean Society of Mechanical Engineering Artificial Intelligence Division since this year. He received his bachelor and PhD in nuclear energy from Hanyang University in 2016 and 2022, respectively. From 2022 to 2023, he worked at KTH Royal Institute of Technology in Sweden as a postdoctoral researcher. And his research interests are computational fluid dynamics and artificial intelligence, with applications in nuclear reactor accident simulation. He is currently developing nuclear reactor digital twin technology through AI-based CFD acceleration with support from the Korean government. Joongoo, thank you so much for joining us this week. And with this short introduction, you can start whenever you are ready.
Okay, thank you, Juan, for introducing me. So, hello, I'm Joongoo Jeon from Jeonbuk National University, Korea. First, thanks for inviting me this fantastic seminar, George and Juan. So today I'm presenting on hybrid solver of CFD and deep learning for long-term simulation, acceleration. So the status and plans of my lab. So before starting the presentation, please unfortunately, I have some sore throat, so please understand if I made some cough in the middle or my voice is hoarse. Okay, so I start. So before starting the main talk, I would like to introduce my research background. So because my major is nuclear engineering, more specifically the nuclear accident, nuclear reactor accident simulation. So as you can see, after Fukushima accident in 2011 in Japan, we noticed how the hydrogen combustion is dangerous for nuclear safety. So during my PhD degree, I developed the hydrogen flammability limit model. So for that, I make some hypothesis on hydrogen flame ignition mechanism, and I verified my hypothesis with computational fluid dynamics, safety. So, and at that time, I realized how expensive CFD simulations are. So at that time, I think we can accelerate CFD with some state-of-the-start AI technology. So actually, I have some simple motivation for my AI research. I want to accelerate the safety. So I developed some framework, I developed some network model and the transfer learning strategy. And luckily, now the Korean government is very interested in developing digital twin for nuclear reactor because we want to enhance the safety and efficiency for nuclear reactor. And for that, we need the digital twin platform. And they think, and also I think, for achieving the very nice digital twin platform, the AI should be the most important for implementing for that technology. So nowadays, with some institute or agencies about nuclear reactor are working on the developing digital twin with scientific machine learning. So here are my contents. So first, I would like to introduce my NILab. So as you can see, this is the normal nuclear reactor. You can understand it, a big nuclear reactor. This is the APR 1000 from Korea. And actually, this is the history of nuclear power plants. As you can see, for big nuclear reactor, we have a history more than 50 years. This pretty long times. So it means that we have enough data for operation, construction or operation, even for accident. So we can having an insight from history. But unfortunately, the nuclear reactor now having a more spotlight is a small modular reactor. So this is from United States and this is from Korea. Give us okay. So actually, there's many advantages for small modular reactor. So we can get more safety, and because we can make a separate module, we can get more benefit from grid simplification. So nowadays, many countries competing on making more dominance for small module reactor market. But there is two main challenging in the small module reactor. So first is the lower cost efficiency due to economy of scale, because the normal nuclear reactor have a very big size, but the small module reactor have a very small size. So there is a reason. And second thing is it is very difficult to verify safety system, because compared to the big nuclear reactor, in small module reactor, we have no operating data. So these two can motivate. We need to develop a small module reactor digital twin platform. So this is the big homework for Korean government, and also I think this is the mission for our lab 9. So actually, I love this picture with the ugly colors. So for getting the nuclear reactor digital twin for the energy safety and efficiency, we need many technology like some solid mechanics and fluid mechanics or like that. And for fluid mechanics, I think safety is a very important pillar for supporting this field. But in safety, there is many gaps. So I think the most representative gap is computational cost. So I think scientific machine learning can overcome these gaps, and we can make a more some fruitful nuclear reactor digital twin. And I think not accelerate. The accelerating the safety is not only for speed. It is also for enhance the accuracy, because if we can accelerate the safety, we can step up from LANs to ADS or DNS from the ADS, so we can get a more high fidelity simulation. So here is the strategy of my lab. So there's a 3-level scientific machine learning framework for small module reactor digital twin. So this blue arrow shows the safety, fidelity of the safety simulation, and this yellow arrow is for scientific machine learning. So as the blue arrows go right, it gains more some high fidelity simulation, and the yellow arrow goes left, it means that we have a more dependency on the scientific machine learning. So the first level is here. So I think for low fidelity safety simulation, we can develop the standalone scientific machine learning. So using single learning, we can understand it like PDA solver. So we can develop PDA solver with scientific machine learning. So you can call it real-time simulator. But in my experience, and also in others' experience, when the safety resolution is more higher, then it's very difficult to some preventing error accumulation from the single training. So at that time, we need hybrid solver. So the second level, I want to call it the safety acceleration. And finally, if we accelerate the safety enough, then using the safety framework with the reinforced learning, we can finding or exploring the optimal flow control. So like this, with a very huge nuclear reactor system. So in summary, the first level is to quickly investigate macroscopic behavior according to design and extent. Because if we want to develop the small module reactor, sometimes we want to change the shape or some component and optimize. And also we should verify it is safe in the extant scenarios. And second is safety acceleration to accelerate high precision simulations. If we can make some macroscopic, some real-time simulator, sometimes we need some detailed simulation for investigating it is safe or not. And third level, optimal control, is to explore control strategies through interaction with safety simulation. So from now on, I will introduce what is the scientific machine learning and safety. So I think everyone already understands this concept, but I want to review that. So let's think about this simple equation in the middle of high school. So there's force and mass and acceleration. And unfortunately, if we learn the university, this equation become more complex. So you can see this is the Navier equation. So this is the pressure and gravity and viscosity. And this is about time differentiation. So if we make a more detail, so this is the left term and right term. So I want to highlight the important thing is we need make a special differentiation and also temporal differentiation. So I think the reason why we need some advanced nuclear numerical scheme is always trying to solve differentiation more effectively. So yeah, so let's assume this is the very simple Poisson equation. So in conventional numerical analysis, there are three methods. First is the finite difference method. So you can think about that this very simple differentiation with a finite difference method. And second, when you take the finite volume method approach, we analyze this equation based on the volume and with the divergence theorem. So you can see that the volume base change to the surface base, and we can solve this equation with the flux. And third, we expect we can solve this by weak formulation. So based on this equation with the basis function, we can make some matrix operation and we can calculate it. So this is the conventional numerical schemes. But I'm very happy because the Crunch Group is the hometown of the PIN. So the fixed informed neural networks is, I think, very good example for scientific machine learning. So as I understood in this technology, first we can order to neural network, oh, please calculate velocity and height. So you can understand the height is the mass in this problem. And then also order, please do differentiate over time. And lastly, we make some loss function and we can order find optimal weight and biases to satisfy these governing equations. So by ordering these three steps, we can get solution from fixed informed neural networks. So this is the actually, I think I love this example. This is the nuclear reactor simulation codes by PIN. So you can see in the finite difference method, you can understand it very conventional approach. They go into the time stepping. So this is the height in the 6 tanks. You can see they stepping the time by time and calculate some real solution. So let's wait until reaching the final value. All right, so we can understand the principle. And PIN is not a time stepping. It is I want to express it the epoch stepping. So you can see this is the true value from the finite difference method. We don't need any data, so they just use the physics informed loss function. So you can see by epoch stepping, they get the real solution. And it's very interesting because in normal numerical scheme, they always making a time stepping and get a solution. But in the PIN, they can solve it by this one whole timeline. So I think it is some good example. So scientific machine learning means that machine learning leveraging our scientific knowledge. So Professor George already published paper with this very nice figure. So how is the first, the observational bias, and second, inductive bias? I think the good example is DeBonet and also my model FVMN. And third is the learning bias, because we can giving information about governing equation to neural network directly. So this is the finished very good example. And also Rapid, which I developed it also using this learning bias. So then why we use machine learning? Why we use the scientific machine learning. So first, we can reduce training data and we can also reduce the training time. And by giving them the scientific some knowledge, we can increase the generalization and also increase acceptability. I think these four reasons are the important, but in nuclear industry, this first reason is very important because in my experience, when I giving them very accurate the neural network model, always nuclear regulatory commission says how we can believe. So this is a very good question. So if we giving them some governing, the governing equations to the neural network, then we can say that because we impose the real governing equation information, so we can believe it. And sometimes they get more agree about that. So I think this is the important things in the nuclear industry. So I think everyone knows what is safety in this seminar. So I briefly introduce. So the safety is the motivation is people always want to simulate fluid to save money and time, and also to validate the experimental result. So scientists always have been developed safety codes. So I think the first try to the making the equation to fluid mechanics is very new equation, but people also want to solve that by spatially and also temporally. So they make a Euler equation, and because Euler equation cannot reflect the viscosity, finally they developed the Navier-Stokes equations. So we first derivation of carbon equations like Navier-Stokes equation, we can use together mass and energy equation, and there's a three normal, the numerical schemes like FDM, FVM. So there's a numerical method for solving PDEs, and third we generate the mesh and making a simulation. So this is the some basic timeline, the pipeline for safety. So why safety is important in nuclear industry is that it's more than 10 years ago, the United States already making the CASA project to develop a virtual environment for reactor application. So they call it ERA because it is not for small module reactor, but also for the big nuclear reactor. We need some digital twin platform to optimize our some system. So in safety, because it's very hard to make an experiment because it's very dangerous. Some benefit of this digital twin platform is very high. So today's talk I mentioned about the 3-level digital twin. So today's talk focus on the first and second levels. Okay, so I already say about the motivation about the unpractical computational cost. So in my experience for hydrogen combustion, for the 1 second physical time simulation, I need more than 100 hours. So, but the important thing is that in for nuclear regulatory, we need 72-hour simulation for our accident scenarios. So let's consider about this. So computing cost, it is very unpractical. And also, if we go into the turbulent region, as you can see in the well reserved areas simulation, it is proportional to the laser number. So it needs more computational time. So for digital twin, so significant CFD acceleration is essential. So first idea is how about thinking of CFD snapshot as some images, because I started my research about 2019. At that time, the AlexNet or other CNN-based deep learning architectures is very some promising technology. So there's two assumptions for CNN. First is the stationarity of statistics, and second is locality of pixel dependencies. To achieve these two properties of CNN, they use this kinds of corner operation. So the corner going to right and down, and they calculate this kinds of output. So we developed the CNN-based deep learning architectures at the first. So this is the autoencoder architecture, and this is the unit architecture. And because we can expect if we use the more time state for input, we can enhance the accuracy. So this is combined with the convolutional LSTM and also unit architecture. So here is the brief result. So at that time, I trained this data about this model about 900 time step. And after 900 step, we tested with the auto regressive manner. It means that after predict from T to T+1, T+1 become input, and we predict the T+2 by output. So as we can easily expect, when our deep learning architecture become more advanced, the error become reduced. But so I can say it works. It works. It's good news. But the problem is that it failed to predict 100 times more when trained with 900 time series. So you can see this is the time step and this is the maximum error. So you can just see this yellow line, the error always accumulated. And the reason is that you can see in the green line, this is the residual value. As in the auto regressive manner, the error is always accumulated. So you can see the scale change about in the heat equation and in the mass equation about 100 times step, they already make a scale change. So, in normal CFD simulation, the scale change means that it become error diverged. So it is very difficult to making a robust acceleration by this technique. So I get back to the first. So the idea of convolution neural net is the image has the stationality of statistics. So you can see using this some assumption from multi-layer perceptron, we can develop the CNN, and they have many good successful in the image field. But let's consider about the CFD. Actually, CFD, we don't need to assume the stationality of statistics because we always follow the same first principle. I mean, the carbonyl equation, like Navier-Stokes equation. So in CNN, because they treat the real image data, they assume the stationality of statistics for the like this all human some faces. But we don't need to assume this statistics because it really identical. So like this Navier-Stokes equation. So we developed the finite volume method network with this. You can see the one grid become one training example because with this one grid with the neighboring grids, we can assume the first order special differentiation. Then we can calculate this output. I mean the temporal differentiation like this equation. So in CNN based, one image become one data set, but in this approach, one grid become one data set. So as I tested, we need about 100,000 images for same accuracy compared to the just 10 images in the FOVML. So this is the same principle with the first phase training, and after that, autoregressively we predict the future time series. So, and this is the training procedure. As you can see in the training part, the one grid and the neighboring grid. So there is 5 information is needed for each variables going to the separated neural network, and they compute the differentiation. I mean the derivative value. So, and at the prediction phase, because we predict this derivative value, we add the previous value and derivative value, so we can get the future time series data. And I want to highlight that I was motivated from the PIN paper at that time. So I added this pixel informed loss function. So the network A is just using the normal mean square error loss function, and B network including this pixel informed loss function. So you can see this is the result. So you can see this is the maximum absolute error for all variables, and this is the ledger. So you can see if we add this pixel informed loss function, the error accumulation some slope become decrease. So this is because I say that when we use the pixel informed loss function, we can reduce the some training amount of training data. In other words, we can enhance the accuracy. So it can predict about 10 times this more when trained with one time series. So the efficiency become significantly increased. And also, as I said, pixel informed loss function can enhance the accuracy. But the problem is the error is still growing. So it is not enough. So, and my point is that this error accumulation issue is not just from my study. These are issues in auto-regressive approach in single training. So you can see this is the CNN-based model result, and this is my result. Because at that time, some issue is that we assume some uniform grid. So when there is a non-uniform grid, we shouldn't need to use some interpolation method. So I think this is advanced approach from other group. So they named it finite volume graph network. So, but the problem is that, as you can see in the time stepping, the error is also diverged at the later pace. So machine learning algorithm, I think, continue to improve, but error eventually accumulate because there is no residual iteration in the machine learning autoregressive process. Because in CFD solvers, they have internal, iteration algorithms and some loop for that, but in the single training machine learning approach, we cannot have it. So I think that's the reason why error always diverges in the single training some approach. So I think this is the problem remaining issue in the autoregressive method. So operator method I think is very smart idea. So this is the also hometown Dibone. So I think it's very nice idea. And I recently checked the paper named Latent Dibone, and they say that the neural operator offers a solution by approximating mapping between this kind of thing, and yet their performance degreed with the system size and complexity. So it means that for more high resolution simulation, it is very difficult to handle it by some vanilla DeepNet. So they developed the latent DeepNet. So I think it's very good idea because using the pre-trained autoencoder, we can use some latent space. It means that you can having a more some low fidelity images to train the DeepNet, and after that we can use the decoder and we can get back to the high resolution data. So it is very interesting. So you can see the compared to the full DeepNet, when you use the pre-trained the autoencoder, the accuracy become more increased. So the use of latent dimension is very innovative, but requires pre-training the autoencoder. So we plan to evaluate the generation performance of latent DeepNet for SMR simulation. So this is some geometry for steam generator in small module reactor. So we want to accelerate this simulation for making the shape optimization, and we plan to apply the latent DeepNet because I think it's the most some advanced technique in nowadays. So I will try. So this is the lessons learned from level 1 scientific machine learning studies. So I think good news is the scientific machine learning really can reduce training cost or training data and also can enhance generalization performance. So this is very good news. But there's also bad news is that in autoregressive method, accumulation of error is inevitable. As I said, the reason is that there is no iteration algorithm like CFD. And in operator method, it is, I think, very nice idea, but the high resolution simulation are susceptible to error. So one of the breakthroughs from the pre-trained autoencoder. But anyway, I think we need some balancing the scientific machine learning and CFD for so getting the more accuracy in the high resolution CFD simulation. So that's the motivation of the level 2 hybrid solver. So I want to introduce the residual-based physics-informed transport learning strategy. I call it repeat. So let's imagine the car racing. So in the car racing, the car go around the track, one track, two track, one by one, and sometimes they can have some more function. So at that time, they going to the repairman. Repairman can fix some car, and they going back to the track. So they can go around again. So I think it's a very similar concept. So you can see in this framework, the first page safety simulation train the neural network. So after that, the neural network going to the track and go around the track very fastly. So at that time, we can achieve some acceleration performance. And sometimes also AI can have a more function. So in other words, it reaches some threshold of the residual. So at that time, we need a repairman, so CFD. So they going to the CFD, and because CFD have a iteration loop for the recovering the residual, they can fix it. And after that, they going to the transfer running and going to track again and go accelerate this simulation. So this going to the machine learning CFD is some cross coupling is continue to the end of this simulation. So I think I can explain in more detail with this slide. So in the traditional CFD, let's assume this is the Navier-Stokes equation, like a momentum equation. So they use the finite volume method in normal commercial CFD software. So they make this equation and they converting it to algebraic equation. And after that, they decompose on this matrix and they can calculate the velocity correction. After that, they get a new velocity value, and with that, they can calculate the flux. And they also can make us a continuity equation. And because this equation going there with this velocity correction equation, we can calculate solve the pressure. So this is a kind of Poisson equation. So we can get the pressure value. And with that value, we can check the continuity errors. So if continuity is more than threshold, it going back to the velocity correction equation, and they get the updated velocity and again doing this loop. And eventually, if they get the lower value compared to the threshold, then they have a final going to the final momentum corrector and get the final velocity at this time step, and then going to the next time step. So this is the traditional safety in the calculating this one time step. And this lipid algorithm, I omit all things about this normal safety. So as summary, with these equations, they get new velocity and new pressure. And they go into the pressure, the machine learning section. So with the new velocity and new pressure is going to the velocity and pressure. And the next time steps velocity and pressure is calculated by neural networks. And during this computation, they made the transform learning. So reducing this new data's mean square error. So with this update parameter, they can calculate the next time series. And they also check the continuity errors. So if error is still lower than the threshold, then they loop in the machine learning section. But at some point, they reach the threshold, and then going to the CFD action again, and they make a velocity corrector, and they keep going this loop. So this is how Refit algorithm can be working on the
Joongoo, I have a question. So the CFD will take as an initial start the machine learning result, because so obviously you don't want to run continuously CFD because it defeats the purpose, right? So so you have bursts of CFD.
You mean in the
short bursts in time. So you have your short burst time. But in order to do that, you have to get as an initial answer the machine learning as an initial condition.
Yes.
Okay, because we've done something very similar for materials, actually, where we interleave TPONet with Memphis, a materials code.
So you mean the machine learning section's initial condition is the whether CFD data or not? So it is true. We use the CFD data for initial condition of the machine learning.
And but also then you use the machine learning as initial condition for CFD.
Yeah, perfect. Yeah, that's right.
Yeah, exactly. Yeah, so you interleave. It's an interleaving. Yeah.
Yeah, that's right. That's perfect. Okay, any question in other papers? Okay, so yeah, so I want to highlight more. So you can see, give me a second. Give me a second. Maybe my word is not unclear. So always safety train the neural net, new safety data, train the transfer learning neural network, and they calculate the next time step depending on using the first last CFD snapshot and going to the time stepping. And also in the safety, the last machine learning time series going to the input of safety, and they repeat this framework. So safety machine learning, they always use the latest data at previous section. So you can understand the use by initial condition. That's right. All right, so I'll skip this. All right, so actually this is some technical things. So I briefly introduced about the detailed lipid algorithm. We use the open form and coupling with the PyTorch. So this is the more detailed some framework. So first, maybe the open form user understand this term. So get solver type from control-dict, and they generate a mesh and run the solver. So and the form data, I mean the CFD snapshot, converted to the numpy arrays because we need the train the PyTorch. So and we already constructed the model. So we train the network and we predict the next time series with the network. So and we check the ledger. So if ledger is lower than threshold and we going to the 9. So and if ledger reach the threshold, we going back to the CFD. So this, I mean, the illustration is more detailed algorithm. So this is the case study. So it's very actually simple case study. So we plan to more the tested more complex. I mean the case study. So this is the left is the hardware, and then the right is the coldware, and this is the adiabatic and adiabatic. So we use the non-slip flow condition. This is kind of natural convection and laminar flow, and we use the buoyancy fin-flip pump, and it's the unified square grids. So actually, it's simple but some tricky. I mean, some difficult case study because the flow mainly only occurs near the boundary. So when we test it by the deep learning CNN architecture, it's very difficult to get a very good, the accuracy. So you can see this. Oh, maybe okay. This is the very you can see the parametrically simple simulation, but it's difficult to train the CNN algorithms. So this is the accuracy performance. So this is single training. So we just trained by initial 3 time series, and they starting to accelerate by machine learning. So you can see with the 3 time series, they mainly may be going to the more for compared to my expectation. They're going to the about 12. It is about 200 time step, but eventually the error accumulated, so there is some ugly result. But in the repeat, you can see they maintain the accuracy from our timeline. So you can see this is some graph, and this is the contour. The figure. So you can see this is the 12. It is quite early space. This is ground truth. So in the single training, about 20 seconds, the single training and also repeat shows the similar result, but in the 20-second, they show some non-physical pattern because they already diverged. So, but in the repeat, they can have some robust simulation. So I believe it is some coupling of the safety and machine learning. So the most interesting is that this is the machine learning section. So in the machine learning section, the ledger always increase, but in the safety section, they can recover the ledger. So it's going up and down like a wave during our timeline. And this is the reference from the open form ledger. So because as I remember, we get insert a threshold of the ledger about 5 times of reference. So when they touch that, they go down because they go into the safety part. So I think it's not a weird simulation because, as you know, this is the normal CFD simulation. In the CFD simulation, they are also having some threshold residual value at the transient calculation. So after in the new time step, they always becoming larger the ledger, but in the iteration loop, they going down and next time step and down. It is very similar with the normal CFD simulation. So a better version of this framework was developed, but to further reduce the computations time, there are 2 hyperparameters we are studying. So first is the epoch for transfer running, because epoch means that we need more time, so lesser the better. So we now testing how we can optimize this epoch number. And second is also the optimal ledger threshold. So you can understand if we get more the ledger threshold, then it's better because they go more step in the machine learning. But if there is too much higher, we insert too much higher residual value, then it can diverge. So we also some studying about how we can optimize this. So today I shown some example about the epoch and the Azure. So in normal CFD, let's say this is you can understand the residual of the some continuity. I mean the mass conservation. So in normal CFD, they get the relative value like that. So this is the iteration value, mean iteration value in the 5 time step, and this is the iteration in the your current time step. So they made this relative ratio. And for example, if we set the threshold to 0.001, if they reach that point, then they going. I mean the before if we set the 0.001, they go into the iteration to reduce more than 0.001. But in our case, because we already set the open form reference, we use that reference value. So the maximum we can make, this is kind of hyperparameter. So if you set this 5 value, so this is the normal residual value in the open form. So they touch the 5, then they go into the safety. So they have this fluctuation. But if you set the more big value like 100, then we can give more time to, I mean, machine learning. So they going about 100, and after that they going back to the safety. So they have some lower frequency. But actually I didn't check that this accuracy is have a robust about the accuracy. But I want to just show that the principle of the residual threshold value is like that. And this is acceleration performance with the epoch number. So you can see because the transport running epochs means that we need more time to train in the intermediate running. So you can see in the 20, we have without pre-training, we have about this require simulation time. About the 2, we have this 237 seconds. And normal open form simulation, we need 450 this amount of simulation time. So with the pre-training included, we actually don't have a acceleration performance, but without pre-training, we can get the acceleration about 2 factor. So I would like to say that if we have a more longer time, then we can neglect the pre-training time. So I expect, and maybe we can demonstrate in the near future in the more long simulation, we can also get this acceleration time, and also we can optimize the epochs number and the residual amount. So maybe in the more complex simulation, I believe we can get more acceleration performance. So someone can ask me why even if you use the machine learning, but the acceleration performance is about 2, not 100 or like that. My answer is that because we always use the CFD and machine learning and cross coupling, so compared to the single training approach, it is very difficult to having a like 100 acceleration performance. But the point is that we can get robust acceleration, not just some few time series. We can get the whole timeline like this acceleration performance. So I think the advantage of lipid is that we can replace this part scientific machine learning model with the set of the art model at any time, like a Lego block. So I think the most the future plan is to use the DeepNet for this framework. So I think this is very advantage. And because in our current neural network FVML need the autoregressive manner, so we need more time to calculate the time series. But in DeepNet, as you know, it is the operator manner, so we can calculate the time at about the 10 time directly. So I think it is very beneficial to use that in our framework. So DeepNet, I think with George and Youngyu, my future work is the DeepNet lipid. So this is the lipid and this is the hints. This is very nice algorithm. So the same thing is we take a hybrid approach and we use the residual based iteration. And so different thing is when to use machine learning and whether pre-trained machine learning is required or not. And I think sometimes we need pre-trained machine learning. So I will try also pre-trained machine learning in lipid strategy. So yeah, I can learn many things from hints. Actually, I can many hint from hints. So actually we can get some very fruitful collaboration between this lipid and hints framework. So this is the conclusion of my today's presentation. So scientific machine learning is the key to develop this tree of a small module reactor. So in worldwide, including Korean government also agree this aspect. So I think we can gather many rules about this mission. And three-level scientific machine learning framework can implement practical and effective digital twin platform. I think reactor real-time simulators continue to advance, but the error accumulation is, the remaining issue. So CFD, SciML hybrid solver like hints or lipid can provide a robust acceleration technique, but in about the lipid, we need more optimization studies for some breakthrough of the acceleration time. So I think the deep neural lipid is our promising topic in future works. Okay, thank you for listening this seminar.
Thank you so much, Jongo. This was a really nice presentation. Do we have any questions from the audience?
Hi. Hi,
Hello.
Jong. It's great talk. My name is Vivek. I'm a PhD student working with Professor George Kaniadakis. So, did you get the opportunity, or were you able to check how the accuracy varies with the computational cost, like in a curve? Does it linearly vary or quadratically vary? Like, could you do a study on that? I see that when you improve the increase the presence of the machine learning model, it becomes computationally more cheaper, but the accuracy falls down. uh, could you do a detailed study with different points in this space of computational cost versus accuracy?
So you mean in my current neural network model, like FVMN, with the accuracy and the time?
Yes, like I saw that the 5 and 100 in maybe 38th slide, I guess. You put the so
Okay, give me a second.
yeah.
So you mean this slide?
The previous one, I guess. Yes, maybe it is good to see how the accuracy varies, like with by varying the 520 all the way up to 100, and see the accuracy and the speed varies on a curve, on a single curve, so we can get an understanding of how it varies. Were you able to do that or not?
Very good question. So actually, this is the in the new result. So until now, I didn't check the accuracy about this 100 residual amount, but in aspect of the acceleration performance compared to the machine learning and safety, as you know, in the machine learning prediction takes about some 0 seconds. So just you can neglect it. So we can just consider about how many time we need in the CFD simulation. So you can see in the 5 or 10, you just think about some frequency is very reduced. So it is proportional to this the frequencies. But the acceleration I should be checked. So later I will publish it from my papers. Very good question. Thank you.
Joongoo, Vivek has actually done this study, and he put in the chat. You can find his paper. It's for materials, but as I said, but instead of CFD, but it's very, very similar actually, and there is a limit because the error eventually will increase. So there is more to it actually, but I think the speed up. What was the best speed up that you got, Vivek? It was 40 or 13.
We went from 2 to 16.
2 to 16. Yeah. So Joongoo is here at 2. Speed up of 2, basically. Yeah. So, but the accuracy also, you have to take into account the accuracy. But the paper
accuracy goes down. Yeah.
Yeah. The paper we put in the he put in the chat. It's very similar to, and you can see there's a follow-up paper also where there's some more improvements.
Right. We in the first paper, we considered like the latent deponent, where we have a pre-trained autoencoder and we train the deponent in the latent space. But we realized when there are small structures coming in, you had to use a unit. So that is the follow-up work and we did more detailed hybridization of the direct numerical simulation with the machine learning approach.
So you mean the chat in the DNS with the machine learning these papers?
Yes, there are two
Oh, okay,
papers.
I will check. So in your study also you predict the time series with autoregressive or operator learning?
We tried both. So we used something in between. So we realized in the second paper, we saw like we use something called like a temporal bundling strategy, where we don't just predict one time step ahead, but just a few time steps ahead.
So this is some kinds of hybrid or just using the single training?
No,
Hybrid,
no,
hybrid.
it is hybrid.
Okay. Oh, I
There
will
is
study more detail.
learning and
Hybrid
the
is exactly like yours, but there's an
emphasis.
improvement so you do something between mapping and autoregression. That's what the time bundling is, and that helps quite a bit.
Yeah.
In fact, in lowering the rate by which the error increases in time.
In the machine learning block.
So
The
it's
DNS
exactly with the problem that you're facing. Yeah.
Oh, I think I can get some more insight from your paper.
Yeah, please. And yes, and one more question. So did you have small structures, or in the problem that you considered, what was the Reynolds number of the flow?
Actually, this is laminar region. Laminar, so very
Laminar.
low Reynolds. So we plan to the test in the turbulent region.
So I have a comment regarding that. We tried doing a similar work where we are considering very high Reynolds number, like 10,000 or 20,000 flow past an airfoil. And we realized using a diffusion model helps stabilize these rollouts, autoregressive rollouts.
You mean because it's very stochastic in turbulent region?
Yes, in the stochastic, there are small scales that needs to be recovered. Spectral bias overall operators from recovering the small scales. And this in turn affects longer rollouts of turbulent flows. So if you bring a diffusion model, it could also potentially help. So, but this is just a comment. Feel free to say.
Thank you. In the turbulent region, I will try that. Thank you for nice comments.
I can put that in the comment as well in a minute or so. Yeah. And great talk. Thank you for your talk.
Thank you. And I heard your exercise performance is more than me, so I think it's yours.
There's a difference because our time scale was small, was a bit larger, so it's in the material science. So there was less of advection and more of a diffusion. Like it was not as difficult as the advection. We were still getting, although the fourth order diffusion process. So second order time, but fourth order in space, but it was still diffusion.
That's a good point, Vivek.
Yeah. So your problem is slightly more difficult. I respect that. Good job. So yeah.
Thanks so much. Let's keep in touch. Thanks so much.
Thank you so much for the questions. Do we have any other questions from the audience?
Yes, I have a question. Hi, my name is Ahmed Peyman. So I'm interested in training the neural operator that you use. How do you train that with what kind of data do you train it? And
So you mean the latent deep neural application in my lab?
yeah, like when you use let's say you're using a neural operator in your solver, and you're taking one time step with the neural operator, right? So do you train it on the same problem? And how do you train it? Do you use the same time interval to train your neural operator there and then use it in the hybrid CFD solver?
Yeah, that's a good question. So actually, I just my plan is using some time rolling the time series and train the deep neural like the first time series is a kind of initial condition, and for example, the predict more than about 10 or 100 time series. So I want to time rolling all the timeline, making the for training the deep neural. But just with my plan. So if you have any more some good recommendation, let me know about some ideas.
Yeah, sure. I don't have any recommendation. I just wanted to learn. So thanks.
Thank you, Ahmad and Vivek. Do we have any other questions from the audience? If not, I think that maybe we can close this week's seminar. Joongoo, thank you so much for your time. This was a really nice
Hold on,
talk.
can
Thank
I
you so
ask
much for
one?
sharing your.
Can I have one question to George?
Yes, yes, Joongoo.
Yeah, George, because now I'm having many insight from Hint. So Hint and latent deep-net. So because in the nuclear reactor simulation also very high fidelity data. So latent deep-net approach is very, I think, promising. But
Yeah.
my question is that your recommendation is using in the LIPI framework deep-net or the latent deep-net with a pre-trained autoencoder, because I think also
That's what Vivek told you. Vivek, that's what we did before, and that was then the genesis of latent deep-net in separate paper. But the first time we actually used the autoencoder with deep-net was in Vivek's paper, and then we wrote this independent paper. But in the second paper, I think he put also the second paper, the follow-up paper is also in Nature Computational Materials. They trained the autoencoder and the deep-net together.
I see.
So that's why yes.
See. So you implement the inside the deep-net to
Right.
autoencoder. See.
I
Now
think
I
Vivek, you have the code on the web, right? So it's in
Yes,
that paper.
both the papers have their codes available. So in the first comment, I have two links actually. Link one is the first paper, link two is the second paper. Then I have the second comment. So the point is that even when whether we train it together or separately, we still observed that when you have the smaller structures, that is larger wave numbers or high frequency structures present, the latent deep-net struggled because using it to learn high wave number content from a low dimensional representation was a very strong constraint for the network to learn. So we put in skip connections and made it a unit, and then it started working. So if you have high wave numbers or high spatial frequencies, then you might have to either increase the size of that bottleneck or start putting skip connections, make it into a unit. So that's the progress in the machine learning side of the hybrid framework we did in Link 2.
Okay, thank you. Perfect. Okay.
Yeah.
Now I got homework.
That's right. Yeah. And one more thing is something that we haven't published yet, but I can cover it in my talk next month in your workshop. Is something called we call Deep O Mamba. So we put Mamba inside the deep-net, and that helps a lot for especially for long time integration. So unlike other methods, we keep the error, unlike on integration, we keep the error constant in time, doesn't increase. So that's very important for this.
Okay, I'm looking forward to seeing
Mamba next week.
Mamba. Okay, Mamba. So next, my target is Mamba. Okay.
Great. Thank you so much, Joongoo, for your time, and thank you so much, everyone, for your attention. And
thanks for staying up today. Yeah.
Thank you, everyone. See you, George and Juan, everyone also.
Bye-bye.